Okay, so beginning today, we will start talking about topics in mid-level processing. Okay, so as I told you in the beginning, there is image processing in general is divided into three parts. That is low-level, mid-level, and high-level processing. And this refers not to the importance of the methods, but to their place in a general image processing pipeline. Okay, so the low level processing methods are sort of the first methods that you will apply to understand the image and its characteristics. In mid level processing, once you have understood some basic characteristics and dealt with noise, in mid level processing, you will try to see the aim of mid level processing is to try and extract the features, important features in an image. Now, the important features in an image, not just for human consumption, but for the consumption of a machine. Okay, which means you want to have a description of those special features in an image. Generally, the special features in an image will be either isolated points or edges or contours of an object. Okay, so these features you want to try and describe using some descriptor which is invariant under some geometric transformations of this image. Okay, so this is the aim of mid-level processing. Hello, does somebody have a question? Hello, either somebody is unmuted by mistake or somebody has a question. Okay, so the aim of mid-level processing is that you want to extract the features in an image and uh, make them useful for a machine to comprehend. Okay, so that is mid-level, and high-level processing is where you use those features and try to derive some um, uh, either a description of the image, maybe using some semantics, okay, or some kind of output which gives some information about that image, okay, which is processed by a machine, and again the information is derived and presented in some knowledgeable form, okay. That is high level processing. So beginning today, we will step into mid level processing, okay. We'll look at, so I will be speeding up a bit, okay, because now that we have covered the basics in some detail, we can use all that language, okay. And in mid level processing also, whatever methods we will see will become part of the language for high level processing, okay. And there are many methods in here, and I will try to cover those which are most important, okay, or which you should know if you have done any computer vision course, essentially. Okay, so some basic and important methods. So as I said, we want to pull out descriptors in an image, and descriptors are mainly lines, edges, contours, these kind of things. So um, So we will look at segmentation. Segmentation means you will want to break up the image into pieces based on, say, some characteristic that is defined. Okay. So usually the characteristic is color. Okay. The characteristic can also be shape. So we want to get to segmentation in some sense. Okay. So one way to, suppose you have decided the characteristic and now you want to break up the image. Let's say you want to break it up into just two parts, foreground or the object and background. Okay. Then this actual breaking up is done by what is called, the process is called thresholding. Okay. So we will look at thresholding today, and thresholding is used in many image processing applications, and as a pre-processing step for many problems. So one of the reasons one would like to do thresholding is because sometimes there is information in the image that you don't really need. You want to push it back in the background, okay, and so that you can work only on the objects of it. Thresholding is also useful if you want to do some kind of morphological operation, because usually morphological, we will see later when I do the lecture on morphology, that morphological operations are set operations that are usually framed in the language of foreground pixels and background pixels. Okay, so you want to have these two classes. So before you do morphological operations, you want to threshold a given image into these two classes. Okay. So in this lecture, we look at thresholding. We will look at 4 types. One basic is this global thresholding. Otsu's method, this is the most commonly used thresholding method. Okay, and we'll see why, for good reason. Then Otsu's method can be generalized to give multiple thresholds. So we'll also look at that. And there is something called variable thresholding. Variable thresholding means, so in all these methods, earlier methods, the thresholds are fixed. Okay, so variable thresholding, so fixed for the entire image. In variable thresholding, the threshold can vary from pixel to pixel or image region to region. Okay, so that's called variable thresholding. We will look at 2 of them, but of course there are many more. Okay, so it's also called as adaptive thresholding. Just like adaptive histogram processing that we saw. No, what was adaptive? Yeah, histogram processing, right? Adaptive histogram equalizations and those things. There are many such adaptive thresholding methods. Okay. But we look at these basic ones. Now, the things to the basic points to remember in intensity thresholding are that one, we want to partition the image into foreground and background based on intensity values. Okay, so that is what thresholding will give you. And generally, the way it proceeds is that if your so you take the histogram of your image, okay, and if the histogram sort of breaks up into two distinct peaks, okay, so the histogram of your image, suppose, looks like this. Okay, it has broken up into two peaks. Then clearly there is a way you can separate. Okay, so all these intensities you can put in one class, and all these you can put in another class. Okay, and then the value where you break is your threshold T. Okay, so if the histogram breaks up like this into two peaks, then that's the best thing, and then threshold is easily chosen. The way you threshold is as follows. So you have an input image fxy. The output image is generated by assigning 1 to all pixels whose intensities are greater than the threshold. Say all of these you assign to 1, and all pixels, all pixels that correspond to these intensities you assign to 0. Okay, so this is a very simple idea. If the histogram is breaking up like this, you threshold them into separate peaks like this. Now the output image you can see consists of 2 values, 0 and 1. So it's called a binary image. Okay, and for displaying purposes, one will usually scale this by 255, so that all these pixels will appear white and all these pixels will appear black. Okay, for displaying it is usually scaled. Now when T is constant, okay, like this, and it is applicable to the entire image, you can threshold the entire image with it. You call the process as global thresholding. And when the value of T changes over an image, this I said earlier, the process is called variable thresholding. Okay, so we'll come to that a bit later. Now, before we start looking more into how thresholding works, here is an important point to note. So there are 2 things that can affect the appearance of the histogram of the image and make your thresholding task difficult. Okay, one of them is noise. So here they have an object here that has only 2 intensity values. Okay, and if you look at the histogram of this image, you can see these 2 peaks. Okay, that means only these 2 intensity values are there. All pixels are distributed in these 2. And so you would obviously, if you want to threshold this image into, I mean, this is already binary, you can assign all of these to 0 and all of these to 1. Okay, and so that's for you can pick up t to be any value between these two peaks and threshold the image. Okay, now if uh, if you actually add some noise to it, so here they have added some Gaussian noise of mean 0 and standard deviation 10. Okay, so now to this image some Gaussian noise has been added. Okay, then the histogram shows, I mean, from it has changed from this to this. Okay, so you can see the change in the histogram and you can look at it and make out that there is some noise. Okay, still this is not so bad, right? You still have two peaks and you could still find a t between these two and threshold the image. Okay, but now here more noise is added. So additive Gaussian noise of mean 0 and standard deviation 50. Okay, so that is the noise level here. And now the histogram looks like this. And so you can imagine, uh, I mean, you can see that you cannot obviously find two peaks and thresholding value to separate them, right? So it is still the same image as before. And you would think, obviously, I mean, to a human, it would appear that, okay, all these pixels should go to one intensity level and all these should go to another. Foreground and background is clear to the human eye. But if you are going to write a thresholding algorithm for this image, then just based on this idea, then it's not going to work, right? So this way, noise can affect the histogram, and it can make, even for images which should be easy to process, which you think should be easy to process, may not be because of noise. The other major uh, contributor to the troubles in thresholding is illumination and reflectance. Illumination means the way the object pictured is illuminated. Okay, what kind of light? It also not just the angle, okay, but also questions like, are there shadows? Okay, so that comes under illumination. Reflectance means reflectance refers to the reflecting properties of the object itself, the object that is being imaged. How is it reflecting light? Okay, so if it's a shiny object, then it is likely that there is a white spot on the object, or a very bright spot on the object. That can create problems in thresholding, because the intensity levels of that black, sorry, the intensity levels of that bright spot may not match the intensity levels of the rest of the object. Okay, and so when you do this kind of thresholding, those pixels are going to be classed in the wrong group. Okay, so illumination and reflectance, these two things play a vital role in influencing the intensity value. So here is an example. The same object as the same image as before, slightly some slight Gaussian noise is added. So this is the histogram. Okay, and now what is being done is it's so this pattern of shading is being added to this image. Okay, so this is a shading pattern which has been obtained. So the histogram of this shading pattern is like this. Okay, so essentially some intensities from 0.2 to 0.6 times 255. So these intensities are being added to this image in this pattern. And then that gives rise to this image. Okay, and you can see how the histogram is affected. Okay, since you have added a darker pattern to the image, all pixels have darkened. The histogram has shifted entirely to the lower intensity levels. Okay, and now you cannot find two peaks like they were in the original image. Okay, so this is a problem that's created by this kind of. So this kind of effect could appear because there is a shadow of something falling on the image. Okay, now this particular example or this particular effect can be easily reversed by to this image you add the reverse of this. Okay, and then you will get back this. So this particular example is easily reversible, but sometimes the effects are not so easily reversible. Okay, like especially these reflectance kind of things, no, where there is a spot of some shiny object that's been imaged and there's a spot on it. Those kind of things create real problems. And shadows create real problems. So one of the best ways, uh, you know, to sort of nip this problem in the bud is at the image taking process, image taking stage itself. If there is something that can be done, then that should be done. Okay. So, for example, I was working on one problem where one had to there were drone images and you have to count the number of plants in that image. Okay, so you this was crop counting. So there were taller trees in the field, and there for some plants there were shadows of these taller trees. Okay, so a thresholding method that worked for the rest of the image didn't work for that particular part, exactly because of the illumination problem. This happens for this is a very common problem. It can also happen that if you take images on a cloudy day and on a sunny day. Okay, you take the image of the same thing on these 2 days. The thresholding, of course, the histogram will be different. So the thresholding that will work for images on one day need not work for images on the other. Okay. So, but I came across this in one conference. So there are these people in Bordeaux who are working on a similar problem, similar kind of plants. They are building a robot that goes around and does weeding in a maize field. Okay. Now, how did they handle this problem? So for them, since they were building a robot, what they could do is they just entirely bypass this problem by having artificial illumination. So it's like a tractor that goes along the rows. Okay, and what they did is they under the seat of the or wherever. So they go one by one. Okay, one plant at a time, and they have artificial illumination. Okay, under the tractor, so that each plant is illuminated by that artificial light, and then an image is being taken. So now they are just completely bypassing this problem of illumination. Okay, so now they can just work through all the images with the same kind of threshold. Okay, illumination and reflectance, both kind of problems taken care of at once. Okay, so this is what I mean. If there is a way in which you can design, or if you have some control over the image taking process, then you should try to get rid of these problems there itself, because it's a pain in pre-processing. These two things cause a lot of pain. Noise is still something that you can do blurring or denoising by various methods and get some respectable results. But these can be really problematic. Okay, so moving on. Yeah, so here one is correcting the shading. So there are, in cases when these cannot be controlled, some of methods that can help are correcting the shading pattern, which is what I said earlier, that you here that you add the reverse of this, okay, to the image and get back the earlier image. Now there is another method which is called the top hat transformation, and we can look at this in some more detail later because it involves this operation which is opening. This is a morphological operation. Okay, so I can talk about this when we have done morphology. Variable thresholding is again something. So variable thresholding, because it will go pixel by pixel and not try to find one threshold for the entire image. Variable thresholding is another way one can go. Okay. However, notice that global thresholding, which gives you one threshold for the entire image, is definitely going to be faster than variable thresholding, where processing has to be done pixel by pixel. Okay. All right. So moving on, let's look at some of the basic thresholding methods. So the first one, global thresholding. In global thresholding, the idea is very simple. You just start with some initial estimate of the threshold. Okay. So the average pixel intensity is a good starting point. So you can take T to be the average pixel intensity of the image. Okay. Then you segment the image into two regions, G1 and G2, using this T. Okay. Now what you do is you look at the average pixel intensity in G1 and the average pixel intensity in G2, which means let M1 be the mean intensity of G1, M2 be the mean intensity of G2. Okay. Now you take the next threshold to be the mean of these two. Okay, so you do some breakup into two regions. Now you look at the mean intensities in those two regions, take their average, call that your next threshold value, and so on. Okay, again with this threshold, you will break up into two regions, take the averages in both average pixel intensities in both regions, and take their average. Continue till the difference in the two successive thresholds is less than a predefined value delta t. Okay, so at each point, you also calculate. So suppose this was t dot and this is t1. So you keep on doing this process essentially till you're not doing any significant improvement over the earlier threshold. Okay, so you can give some epsilon, some delta t, and say if the improvement is not above this delta t, then we'll stop and we'll call that as the threshold. So this is global thresholding. This is automatic. I mean, which means it can be automated. Okay, you don't have to do it, by hand by looking at the histogram. Okay, here is an example of global thresholding. Okay, so this is the given image, and this is the histogram of that image, and just using this global thresholding method, good threshold is found. And did they say what threshold? No. And then segmentation. This is segmentation where the original image is broken up into background and foreground, or regions, that is object of interest and objects not of interest. Okay, something like that. Background and foreground. Okay. This is global thresholding. This is very straightforward and one of the easiest ways of thresholding. And the point to note is that this algorithm will work well when there is a clear separation, okay, between the peaks of the histogram. Okay. Well, what is the difference between doing it manually and doing it with global thresholding? There is no difference really. The only thing is if you're doing manually, image by image, you are assigning the threshold. Global thresholding is doing the same thing automatically. That's the only thing. So this will work best if you have two peaks like this. If you don't have this, then global thresholding doesn't do a good job. Okay. Yeah, just some note about convergence. Then let's move on to Otsu's method. So Otsu method is one of the, so it treats thresholding as an optimization problem. Okay, and in general, thresholding can be thought of as an optimization problem. Okay, so what you want to do is you want to minimize. So suppose you have your input image fxy. Sorry, input image fxy. Okay, and the pixels of f you have assigned values gxy now. Okay, so fxy has become gxy. So so now after some thresholding, sorry, so this is being done after some thresholding. Okay, then you can measure the average error that is that comes about by assigning these pixels into these two classes. Okay, so this is in general you can think of thresholding this way. So you want to minimize the in-class variance. I hope I. So what I'm saying is, let's look at this simplistic example. Suppose you found a threshold here. Okay, so these pixels are being assigned to 0 and these pixels are being assigned to 1. Correct? So now you find the average error in this assignment and average error in this assignment. The best threshold will minimize these average errors. Right? So that way you can look at thresholding as a minimization problem. But that problem, even though it has theoretically it has a closed form solution in terms of this Bayes decision theory, finding those PDFs is not an easy task. Okay, so this Otsu's idea is to approach this problem by, instead of minimizing the in-class variance, you try to maximize the between class variance. Okay, so in what is this called? This discriminant in discriminant methods, statistical discriminant analysis. So there's something called as in class and between class variance. Okay, so if you have not heard of this, also you don't need to worry. Essentially, what we are saying is that suppose you have some data and you have clustered it into some classes. Okay, this clustering you want to do it in such a way so that for points in the same cluster, the distance between these points is minimized. Okay, this is true for every cluster. The distance among points in the same cluster is minimized, and the distance between clusters is maximized. Okay, or distance between points in different clusters is maximized. Okay, so the distance between these points is maximized. Okay, so if you're looking within a cluster, that is in class, and between clusters, that is between class. Okay, so that's the simple idea. So instead of minimizing the in-class variance, Otsu's idea is to approach the problem by maximizing the between-class variance. Okay, which means you try to threshold, or you try to find groups of pixels, so that if you group the pixels, say as group 1, group 2, group, you later we'll see 3 also we can do. Okay, so if you group the pixels into these 3 groups, then the distance between the distance, again, you can measure with some norm. So the distance or the separation between the pixels in this group and this group is maximized. Okay, this is true for any 2 pixels in the group. Or this is true for any 2 pixels, I should say. Okay, the between class distance is maximized. So that is this idea. Look at this problem as a maximizing the between class variance problem. Okay, so let's see how that is solved. So let's assume that you have an image with 0 to L minus 1 intensity levels. Okay, and the digital image of size m cross n we will fix. Now let ni be the number of pixels with intensity I. So that's going to be exactly at level I, the bar that you get in the histogram, right? That is going to correspond to ni. So ni is number of pixels with intensity I. Then the total number of pixels is just the sum of all these ni. Then if you recall, the normalized histogram of the image will be ni over mn, right? This ni divided by the total number of pixels, and that leads to these 2 things. Okay. Now suppose we want to partition the image into 2 regions, C1 and C2. Okay, foreground, background. Let's call the regions C1 and C2. Suppose you choose some threshold K. Now with respect to that threshold, let's compute the probability of a pixel lying in class C1 and the probability of a pixel lying in class C2. Okay, so the probability that a given pixel lies in the class C1 will simply be summation pi from I going for I going from 0 to k, right? Because you remember how the breakup is being done. Up to k, up to intensity levels k, you're putting everything in class C1, and intensity levels above k plus above and equal to k plus 1, you're putting in class C2. So if that is the thresholding, then this is going to be the probability that a given pixel falls in the class C1, probability that a given pixel falls in the class C2. Okay. This is for a fixed threshold K. Okay. And these are just the mean intensities of the pixels in C1, mean intensity of pixels in C2. Right. So then one can define what is called as the average intensity of the image, average or global intensity of the image using these probabilities, right? So in general, the average intensity of the image is just the sum of all intensities divided by the size of the image. Okay, but in terms of these probabilities, you can think of it as summation IPI. Now, these are two things that you can easily, this one obviously, and this one also you can verify that P1 times M1 plus P2 times M2 is Mg, right? Then, if sigma B square denotes the between class variance, so you have fixed the threshold K and you have obtained these quantities, okay? Then with respect to that threshold, suppose sigma B square denotes the between class variance. So the formula for between class variance is given by this for two classes. Okay, so this is the formula for between class variance. So these steps I have skipped, but you can easily check using these two properties. Okay, that sigma B square gets simplified to this quantity. Okay, mg times P1 minus m whole square divided by P1 times P2 or P1 times 1 minus P1. Okay. Of course, I'm assuming here we are going to assume that this capital P1 and capital P2 are both non-zero. Okay. We will have the assumption that P1, P2 are both strictly greater than 0. Okay, so with that assumption, sigma B square can be written in this form, okay, with these quantities being defined as earlier. So the point to remember is that all this was done with respect to a fixed threshold K. Okay, so you can actually think of this as a function of K. So that's how what I have written here. Everything here is a function of K, in fact, right? Once you decide a threshold and you divide into these two classes, then you are getting all those probabilities. So essentially, everything written as a function of K looks like this. And what we want to do is find the threshold K which maximizes this function, right? So the optimum or required threshold K star is the value of K that maximizes sigma B square K. And now the thing to remember is that these are discrete values. No more a continuous function. These are going to be all discrete values. So simply you have to find among those finite number of discrete values, you just have to find the largest one. So you simply evaluate sigma B square K for integer values K, all of these, and find the maximum. And then the corresponding value of K is the required K star. Okay, so that is how this optimization problem is solved. So you will find the threshold K star which maximizes the between class variance for a given threshold. Okay. And there is a way of checking what is the effectiveness of this thresholding. You simply divide the sigma B square that you obtain by the global variance. Okay. So obviously this quantity is going to be between 0 and 1, with 0 being when this is absolutely ineffective, okay, and 1 being the case when there are exactly two classes that you are breaking up. I mean, where there is a very good threshold. Okay. So higher this quantity is, the better it is. Yeah. So this is Otsu's thresholding essentially by optimizing this function sigma B square. Okay, and the way it is implemented is straightforward. You compute the normalized histogram of the image, compute the cumulative sums P1K and the cumulative means MK, okay, for every K. So you do this, you just find these for every value of K between 0 and L minus 1. Okay, and then you just find the maximum among all those computed values. Okay, so you just find that the required threshold is the one for which sigma B square K is maximum. If K is not unique, if there are two such values, then you take the average of all the Ks for which sigma B square is minimum. That is how the tie is broken. By taking the whatever, if you get more than one intensity values as the threshold, you take their average. Okay, so this is Otsu's algorithm and is one of the best algorithms for thresholding. and is implemented in NumPy and MATLAB and many other, I mean, any library that deals with image processing techniques, you will have outsource algorithm. Okay. So here is an example that shows the effectivity of thresholding by outsource algorithm. So here is the original image whose histogram is this way. Okay, so you can see global thresholding is going to be no good here. Now, yeah, so in fact, they have done this is global thresholding, and this is what outsource thresholding gives you. Okay, so if you were interested in these objects, okay, and you wanted to break this image into foreground and background, then outsource thresholding gives you a pretty good approximation to it. Okay. Yeah, any questions about outsource thresholding? Okay. So, by the way, you will have occasion in your homework to look at these ones applied to different images. Okay. In fact, if you don't know which thresholding to use in a given thing, the first thing to try is just outsource threshold. Okay, it's called outsource thresh in Python. So you can, that's the first thing you should try. Then multiple thresholding. Multiple thresholding means you can apply outsource method to divide into more than two classes. These are just two classes of pixels, but you can also choose to divide the image into more than two classes of pixels, applying the same ideas as you saw here. Okay, so instead of two classes, you will have three or more classes. So if thresholding into k classes, C1 to Ck is desired, then you just have to get your variance formula accordingly. Okay, the between class variance for k classes is, this is the formula. Okay, and by the same procedure as before, but now you know, if you want three classes, then I mean, you will have to maximize in all three directions. Okay, k1, k2, k3. So that way you have to just be careful about the indexing in this case. So the required thresholds k1 star, k2 star up to k minus 1 star are values that will minimize this, not minimize, maximize this expression. Okay, so here is a small example. If k is equal to 3, suppose, which means you want to break up the image into 3 classes. Okay, then you want to find k1 star and k2 star, right? Two thresholds which will break up your image into 3 classes. Then you start with a value of k1. I mean, you just take some value of k1. I mean, you will evaluate for all of these, right? So for all these values of k1, you evaluate this expression. Okay, and then for every fixed value of k1, you increment k2 through values between between k1 and l minus 1. So if k1 is 0, then you evaluate this expression for, so you will evaluate sigma b squared 0, and k2 varies from 0 to l minus 1. So all of those you will list. Then you will evaluate sigma b square. Now you put k1 is 1, and k2 varies between 1 and l minus 1, and so on. Okay. So in the end, you have a matrix of values this way. So if k is 3, that means you are seeking through two thresholds. Your data is arranged in a two-dimensional matrix. If k is larger, okay, if k is 10, let's say, and you want to divide, then you require 9 thresholds. Then you will have actually a 9-dimensional tensor. Okay, not a matrix like this. Okay. Anyway, so but if these are all discrete values, you will just go through each of them one by one, and then you can find the max. So here is an example of multiple thresholding. So this is the histogram, and also thresholding has found, I mean, this histogram is also good enough. Even manually, you could have found these. Anyway, so this original image is broken up into these 3 groups. Okay, the pixels are broken up into these 3 groups. Although there are a few white pixels here, so they are actually grouped like this. Okay. So that's multiple thresholding, and here I've just written exactly how the threshold and image will look like. Yeah. Then we can move to variable thresholding. Variable thresholding, as I mentioned earlier, is you find thresholds for every pixel instead of for the entire image. Okay. So when global thresholding methods are not working out, then this is the thing to try. There are many variable thresholding methods, and we will look at just two simple ideas or basic ideas. One is the idea based on local image properties. Local image properties means you could be using mean of a neighborhood or standard deviation in a neighborhood, okay, or Gaussian in a neighborhood, these kind of things. Okay, so I think I have written, yeah. So for a pixel xy, choose a neighborhood nxy, okay, and let mxy sigma xy denote the mean standard deviation of pixel values in that neighborhood. So you fix a pixel, fix a neighborhood, look at the mean and standard deviation in that neighborhood, and you define a threshold for that pixel position, okay, or for that pixel as a linear combination, some linear combination of this mean and standard deviation. Okay, so this a and b can be some constants. Another commonly used threshold is, you take a linear combination of the standard deviation and the global image mean. Okay, so and there are more also. I mean, these are just two examples of how you can use neighborhood statistics to define a threshold for a pixel. Okay. Thresholding is done as usual. Okay, you say if the pixel value is greater than this threshold, I will assign 1. Otherwise, at that pixel position, I will assign 0. Okay, so see, this is pixel wise. It depends entirely on the value that you have computed at that pixel. There are other ways also. So this was using neighborhood statistic. You can use predicates, which means you can let qxy be some function of the local parameters. Okay, and then you just decide to assign 1 at xy if the predicate holds, and 0 if the predicate does not hold. Okay, and finally Gaussian, which means you sort of take a you are actually taking a weighted mean of all pixels, and those weights follow a Gaussian. Okay, so this is one more way in which you can decide what the txy should be. These are just some examples of using local image properties to decide what the threshold at every pixel should be. Okay, and another commonly used idea is this idea of using moving averages. Okay, so maybe you have heard of moving averages before, but even if you have not, this here is the definition of a moving average. Okay, but essentially what happens is this you can show. So for moving averages, actually, first I should say that the way this is done is so suppose this is what k plus 2 minus n, right? You want to take the sum of zi from zi or intensity from k plus 2 minus n to k plus 1. So uh, first, the image is considered in linear order. Okay, either like this row wise. So this is z1, z2, z3, z4, and so on, and then the next row, and then the next row, and so on. Okay, you can linearize either row wise or you can linearize column wise. Okay, so one of these linearization methods is followed. So you have a linear ordering on the pixels of the image. Once you have that linear ordering, and now you want to apply this formula, if required, you pad it with some zeros in the beginning. Okay, if the formula calls for it, you add some zeros. And then it turns out that this formula for moving averages is actually a recursive relation. Okay, so you can show that mk plus 1 is mk plus 1 over n times zk plus 1 minus zk plus 1 minus n. So there are some details here, but you can also easily show it from this. The point is, the formula for moving averages is a recurrence relation. So once you have calculated mk, you can calculate mk plus 1 from this formula. Okay, so the computation is not too difficult. And then typically something like this, some scalar times the moving average at xy is used as a threshold. Okay, so this is how moving averages are used, and here are some examples of images. So this is the one where they are using local thresholding. I think image segmented using dual thresholding, image of local yeah. So this is the original image. It obviously, if you're studying this and want to segment this, you would want to threshold this as, you know, these white dots appearing in one level, these gray regions appearing in another level, and background appearing in another level. You would seek that kind of thresholding. Okay. So if you do thresholding using OTSU, multiple thresholding, this is the result that is appearing. This is the result of local standard deviation. So local thresholding using standard deviation gives this. Okay. And this is also using some local thresholding. So sorry. What is being done? So this is local standard deviations. And then, oh, so I see. So these are just the local standard deviations plotted in an image. Okay, this is not thresholding actually. These are just at every pixel, the standard deviation has been calculated over some neighborhood, some fixed neighborhood size is fixed, and that is being plotted as an image. Okay, so this is the image of local standard deviations, and those being used for thresholding, the result of that is here in the last image. Okay. So this is what OTSU gives, this is what local thresholding gives. Of course, which you want, which one of these you want depends on what application you're looking at, or why you are analyzing this image. Okay. Here is another example of adaptive. So this one is using moving averages. Okay. So this is the original image, and you want to sort of remove the effect of these shadows. Okay. Then this is the effect of Otsu's method. Okay, it's just losing some of this data here, right? So Otsu's thresholding is absolutely no good for such an image. However, if you do moving averages, then this is, so from this image, this is exactly what you would expect, right? Improving the quality of this image would be getting something like this. So thresholding using moving averages is having this effect of removing the shadow. Okay. Another way would be to subtract exactly this kind of the reverse of this kind of shading effect. Okay, if you did that, even then this would be obtained. Okay, does anybody have questions? So we have 20 minutes and I'm done with thresholding. What we can do is move on to the next topic, which is feature detection. Okay, so feature detection. We will not go into like entire details of feature detection, but we will look at the basics. Okay. So feature detectors and descriptors, as I said earlier, are used to analyze, describe, and match images. Okay, these are also used for matching. And for some examples of these are, you know, image stitching, when you want to identify key points or feature points, and then match those images. Okay, so I've referred to Zaleski's book here. So, like this example. Okay, or panoramic. So I remember in 2005 or 6, this came in, or 7, I don't know. Around that time, image stitching came in Google Photos, right? And so you could, if you these panorama images started getting generated, right? So the way panorama images work is by image stitching. So what is done is so this is not an example of image stitching. Sorry. Here, this is just I'm trying to say you want to find matching points in these two images. Okay. So these two images are of the same place taken from slightly different angles. Then which point matches with which point here? Okay. So finding a set of matching points. And in this way only image stitching is done, by finding a set of matching points, then overlaying them. Okay. This is another example of images where you want to find a set of matching points. So here, if you can identify which edge corresponds to which edge. Okay. So the various edges that correspond to each other, not just corners, but even edges, then that gives you a better set of matching points. Okay. So for objects where there are such straight lines, corners, okay, those are good objects for matching. For obvious reasons, you can pinpoint the key points much more easily. Okay. For images like this, it's a difficult task. Okay. Finding key points to match is a harder task for images like this, where you don't have any obvious straight lines or corners or things like that. Okay. So the general key point detection and matching pipeline works in the following manner. First, you detect and extract the features. So just detection is not enough. You also need to extract it. Extract means you want to put it in some form which is compact and stable. Okay, generally in some vector. Okay, you want to put all these the features that you have extracted. You want to arrange them in the form of a vector, so that that vector is stable, which means invariant under certain operations. Okay, if you change the image a little bit, then the vector shouldn't be changing. Okay, so that's what we mean by invariant. So the region around each detected key point is converted into a compact and stable descriptor that can be matched against other descriptors. Then the step is feature matching, which means so you have these candidates for key points, and corresponding to each candidate you have a descriptor. Now you see which descriptor is close to which other one. Okay, that's feature matching. And if you are doing video processing, something that we are not looking at in this course at all, in video processing there is also feature tracking, because in video processing what happens is in subsequent frames, okay, there will be only little difference in the images. Okay, so you can actually track a key point through those subsequent frames. Okay, so that is feature tracking. Well, so there are three main types of image characteristics which we try to seek out, and these are particularly useful for being treated as features: points, lines, and edges. And all these are characterized by sharp changes in their intensities. Okay. So edge pixels are pixels at which the intensity of an image changes abruptly. Okay, and so this is the language we will use actually. And so that is why I've just written it down. So edge pixels are pixels where intensity has changed abruptly. Edges means the set of all such edge pixels that are connected with each other. Okay, so sets of connected edge pixels are called edges. Connected simply means they form a contiguous set. Okay, so here is a pixel and this one is connected to it and so on. Okay, however, this will be one edge and this will be another edge. Okay, they are disconnected. So connectivity is simply what you would think of it as an English word. So edges are sets of connected edge pixels. Edge detectors are local image processing techniques which are designed to detect these edge pixels. Okay. Then a line for us will be a thin edge segment such that the intensities on either side of the line is either much higher or much lower than the intensity of the line. That is what we will mean by line. Okay, a thin edge segment, edge means again in this sense, okay, such that the intensity on the two sides of that edge segment are either much higher or much lower than that of the line itself. An isolated point is a foreground pixel surrounded by background pixels or vice versa, something like this. Okay, so suppose this is a background pixel surrounded by foreground pixel, or the opposite situation. That is the definition of an isolated point. So we'll see how to detect isolated points. This is quite straightforward. You use Laplacian and then do thresholding. Okay, so why Laplacian? So, well, here I have just outlined the process. Okay, you convolve the image with a Laplacian kernel and use a threshold T to do the thresholding. Okay, so we'll see what threshold. It will depend on the output of this output of the kernel. Okay. So the idea is that the Laplacian measures weighted differences between a pixel and its 4 or 8 neighbors, depending on what Laplacian you take. If you take this Laplacian, you're focusing on 4 neighbors. On the other hand, if you take this Laplacian, you're focusing on 8 neighbors. Okay. So depending on this, the point is that if you convolve an image with a Laplacian, then at each location, you're sort of taking a weighted sum of its neighbors. Right? So now if you have an isolated point, which means, so here, this is an example where this is an isolated pixel because this has an intensity that is different from all its neighborhoods. So you can think of this as being an object pixel and these as being background pixels. Okay. So, I mean, in the real world, I mean, if you plot this as an image, you might not even be able to recognize. But okay, just as an example, this is an isolated pixel. Okay, now suppose you apply this Laplacian to this. The result of convolution is going to be this array. Okay, so you can imagine when this is constant, since the sum of the elements of this Laplacian or of any Laplacian, the sum of elements is 0. So when you're calculating it for a pixel whose 4 neighborhood has the same value, then there's going to be no change. Okay, in fact, you're going to get a 0 because we have a -4 here. So on an area of constant intensity, the Laplacian is going to give you zeros. Or the only changes are going to occur when there is something different in the neighborhood. So turns out that you get these kind of numbers, okay, and when the Laplacian is placed at the center, that's when you get the largest change. Okay. The thing to note is that and this is true actually in many cases, that after convolution, usually you might end up with numbers that are not between 0 and 255. So it's very common to you can either threshold directly by taking some t between this and this. Okay, so you can do it that way, or you can scale this image, okay, between 0 and 255, and then do threshold. So either way, you can do this. Okay, and this is what I have said earlier here. Okay, you choose the threshold t, and whenever mod gxy is greater than t, mod gxy means mod of these entries that you've got here. Okay? If it's greater than t, you assign 1, otherwise 0. So this is how you'll get a binary image by threshold. Here I've chosen 100. Okay. You can check what happens if you, instead of this Laplacian, you choose a 8 neighborhood Laplacian. Okay, you can work out the same example and see what will happen. But essentially, I mean, you might probably guess, right? First of all, the numbers will change, but also you might get some non-zero entities here. Okay, that is okay. So this is how you can detect an isolated point. So this was an isolated point here, and doing this process gave you a binary image where the isolated point is black pixel on a white background. Okay. So this is isolated point detection. Line detection. So in line detection, or in any edge detection, we will make use of both the first and second derivatives. Okay. So there are few things to be observed on the intensity profile of a scan line in an image when that scan line passes through edges or lines. Okay. So these are observations about the first derivative. Okay, so the first derivative is non-zero at the onset and along the entire intensity ramp. Intensity ramp means a place where the intensities are rising or coming down steadily. Okay, so this is an intensity ramp in the intensity profile. And the second derivative is non-zero only at the outset and at the end of the ramp. Okay, so these things I think I had discussed in detail in one of the earlier lectures. We had looked at this kind of thing in much detail, right? How the first derivative is calculated, how the second derivative is calculated, and so on. And so these observations that I have listed here are simply saying that, you know, along the ramp, you will have that the first derivative remains constant. So this is the ramp. Yeah, that's the only ramp here. Okay. So at the outset and here, that's where it changes. Okay, and it stays constant. On the other hand, the second derivative is zero along the ramp. Okay, and at the beginning of the ramp and at the end of the ramp, it has some jump. Okay, there is a jump here and a jump here. So this is how a ramp can be detected from first and second derivatives. Okay, so you see both these behaviors, then you can guess that it must be coming from a ramp. Okay. Similarly, what happens at an isolated point? Isolated point means, so actually this is the image and they have taken the scan line here and taken the intensity profile along this scan line. Okay, so you can see what is happening. See, in the beginning, these are a bit gray pixels. Okay, so the intensity values, they are taking only 8 bit. So suppose the intensity values are here. Okay, then they are becoming darker. So the intensity is going down. Here is an isolated point. Okay, so at the isolated point, the intensity jumps and then comes down immediately again. Again, dark pixels, and here is a line. Okay, so what is happening at the line is that you have a behavior like this, right? The intensity jumps and then comes back, but not as quickly as the isolated point. Okay, there is some width to this line. So that tiny thing is here. And then you have dark pixels again and lighter pixels. So dark pixels suddenly move to lighter pixels, right? This is a quick change in the intensity, and that leads to this step. Okay, so these are the various features, and you can see them in this intensity profile. You can sample this intensity profile and take finite differences to calculate the first derivative and second derivative. Okay, and from the behavior of the first and second derivative, one can sort of infer what are the what are the features in this image. Okay, so that is the idea. Okay, so here I have just listed all these things that if you have a region of constant intensity, then the first derivative is 0 and constant, and therefore the second derivative is also 0. If you have an isolated point, then there is a change in sign at the first derivative and a sharp change for the second derivative. Okay, if you have a line, almost the same conditions as those for an isolated point, right? Because in fact, here also we saw this is, although this is not as quick a jump as an isolated point, it is still the same shape and characteristics. So if we look in terms of the first and second derivatives, we can see the sort of the same characteristics appearing here. And an edge is an intensity step up or step down. So that corresponds to a sharp change in the first derivative and a zero crossing in the second derivative. So zero crossing, I had explained in some detail earlier, but essentially feature like this, where you have this. Okay, so positive value turning into a negative value or a negative value turning into a positive value. That's a zero crossing. So this is the characteristic of an edge. Okay, so this is a line, this is an edge. There's a difference between line and edge. So we defined a line as sort of an edge such that on both side of it, the whatever the intensities are there on the line, on either sides of it, the intensities are opposite. Okay, but this is an edge. Okay, where there's a sharp change in intensity. So we differentiate between lines and edges this way. And edges are characterized by this step. Either it's step up or it could be the other way, step down. Okay. And in terms of derivatives, the behavior of the second derivative, this is called zero crossing. Okay. That is what characterizes an edge. Okay. So zero crossing. All right. So here is a quick view of the types of edges. Okay, one is a roof edge like this. Okay, this will model lines passing through a region. So it is called a roof edge in the ramp. Okay, so like this. But essentially what it models is lines that pass through a region. A ramp edge, okay, this is where you have a ramp like this, okay, which corresponds to a region of slowly changing intensities. That is what the ramp corresponds to. Okay, so it's called a ramp edge. So these model blurred or slowly transitioning edges, and a step edge which models sharp edges. Okay, so there are these three kinds of. Again, this is part of language only, and I have just for your benefit, I have just drawn the intensity profiles of each of these and the first and second derivatives. Okay, so for example, even in a ramp edge, you will see a zero crossing, but that will occur over a period. Okay, whereas if you have a sharp edge like this, then the zero crossing appears almost consecutive pixels or consecutive sampling points, like here. Okay, so here also we had this, right? -1, zeros, and then 1. So there will be a zero crossing because of this also. Whereas here it's a quick zero crossing. So this is a sharp edge, whereas this is a ramp edge. Okay. So I'm almost at the end. So coming back to this Laplacian kernel that we saw earlier. So if you remember from before, the Laplacian kernel is isotropic, which means if you rotate it by depends on which one you're looking at. If you rotate the 4 neighborhood Laplacian by 90 degrees, this one, it is isotropic under 90-degree rotations, whereas this one is isotropic under 45-degree rotations also. Okay. Anyway, we'll just say it's isotropic. So its response is independent of direction. Okay, so it's not the best one to, if you're looking for lines or edges which have some direction. Okay, so the better way is to look at these kind of kernels which are called line kernels. Okay, because so for example, this kernel is good at detecting horizontal lines. Okay, because simply because more weight is being afforded in the horizontal direction. Similarly here, this will work better for this kind of angle. This will work better for vertical angles. This will work better for these kind of angles. Okay. So these are called line kernels. Another thing to note about the Laplacian is this double line effect. Okay, double line effect means what? Actually, I'll just show you the image. So if one takes the Laplacian of this image, okay, then this is how the intensities look like. Okay, so in the original image, yeah, here, this spot they are looking at, right? So this spot. So in this spot, what is happening is there's a sharp change in intensity. Okay, so that sharp change in intensity, when you take the Laplacian, it will appear as a dark pixel, a line of dark pixels and a line of light pixels. Okay, so you will get this two-edge effect when the Laplacian is taken. Okay, and this is sort of a characteristic of the Laplacian, just to keep in mind. Okay, this is every edge under the Laplacian will correspond to a double line. Okay, and the transition, whether it will be from light to dark or dark to light, depends on whether. So, edge is at a zero crossing. So, if the lighter pixel came first, then sorry, if the darker pixel came first, like here, okay, then you will have a positive first and negative next. And if it's vice versa, if the lighter pixel came first, you'll have a negative first and then a positive. Okay, and if you plot that as an image, then it will look like this. If you plot the Laplacian of this as an image, you will see this double line effect. All right. So I think that was the end. Yeah. So this was just a quick introduction to various feature and feature detection. Now we will go into some more details. Okay, so we have done thresholding. The next thing we'll do is segmentation and various methods, and then we want to go into edge detection and various edge detection methods. Okay, and then we will also look at some more segmentation methods using things like watersheds, or there are many methods. So we will look at a couple of those at least. Okay. So that is what we will do. Yeah, sorry. And then the most important thing is key point matching algorithms. So there is this algorithm called SIFT, the shift invariant feature transform, which is one of the most successful algorithms in the being used in the industry for key point matching. Okay, so we will take a look at SIFT also. Okay, so I think that is already quite ambitious for mid-level processing for our course. Okay, and then we will move into some high-level processing. Okay. All right. So if you have any questions, you can ask me now, or we can stop.
Ma'am.
Yes.
So when will be our next quiz?
Yes. So there has been a discussion on the group, right?
Yeah.
I will just I will announce that in Moodle.
So actually you mentioned about 15th April, but I guess 15th April is a holiday. It's Good Friday, so
that's okay. I think it's not such a big deal. It's half an hour of a quiz.
Yeah, but actually, so in that weekend, so we are getting some long holidays, so that's why we are making some plans about.
Okay, look, yeah, you can have your plans, but this discussion we have been having over 2 weeks now, right? Almost from the last quiz. Now suddenly you cannot tell me that it will not work, because I cannot find dates this way.
Okay.
Right? I mean, you could have put both objections right then, no?
Yeah, sure.
Now
That
you
was
cannot.
not sure, so that's why we are.
What do you mean not sure? I mean, how else is it going to become sure if not by discussion with the class? Am I going to come up overnight with some other date? I'm asking you guys only, no, what to do. I'm asking the entire class what is a suitable time. So that discussion, how old is it? Nobody has like raised any concerns about this. Okay, this was already on 3rd April. And I said, yeah, we will go by that schedule. I will declare it on. So it's already done. You can do your trips and whatever you want to do. Just be sure that for half an hour you are online. I can do any half hour that day and take the quiz.
Okay, ma'am.
And for people who are on campus, this is only about off-campus people, right? People who are on campus, what's the big deal?
So I am in campus actually. So
Oh, yeah, what I mean,
yeah, sure, ma'am. Okay. Time on that.
you then see if I ask you to come up with some day, no, that's never going to happen. It won't happen till 15th April.
Yeah, yeah.
Like this is what happened the previous time also. Okay, previous time it was because I had a issue, so I had to cancel at the last moment. So
Yeah, ma'am. Sure, sure.
see, it's the beginning, right? 15th is the beginning of a long weekend, right? We can do it early
So
morning on 15th and get over with.
the
Or
14th
we
is
can do on
starting, right?
14th. Okay, so 14th is working day. If everybody is okay, I am willing to do it
Yeah.
on 14th and get
14th or
over with.
can you make it on 13th? So 13th is
No,
Thursday.
no.
So
Uh,
Thursday.
14th is Thursday, no? What's the problem?
Okay, okay, okay. 14th is Thursday. Okay, right, right.
14th is a Thursday. It's a working day, and we can have it on 14th during class time.
Okay, ma'am. Okay, sure.
Okay, so class time is definitely time that on a working day in class time is something that everybody should be able to do technically. Okay.
Okay, ma'am. Yeah, 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 right. Cool.
So 14th class time in class, we will take the quiz. This is not an open book quiz. You will come to class and do it if you're on campus. If you're off campus, then I have no control. Okay.
Okay. Yeah.
Yeah. So let's do it on Thursday, all right? So now
Yeah.
don't make any changes. I'm in fact to preempt all that, I'm going to make the announcement on Moodle in 5 minutes because then we have 2 more to go, right? When will we find time for that?
Yeah.
Yeah. Yeah, but if you have any objection, so this was legitimate objection. I am not saying it is wrong that it's a holiday. Fine, it's a legitimate objection, but don't come up with it very at the last moment. Like last time also somebody wrote to me in midnight. This is a midnight message somebody is sending me on the day before the quiz that there is something else scheduled at that time. How can this happen?
Yeah, yeah,
This
right.
is yeah. This is so you think about the other person also, right? From my side also, it's not easy to change things at the last moment.
Okay.